Yeah, so I'll be talking about an energy conserving upwinded compatible finite element discretisation for the dry compressible Euler equations. And that's work I did together with my supervisors, Colin Cotter and Werner Bauer at Imperial College. Right, so I'll first talk about the ingredients that I'm using here. So I'll use the compatible finite element method, and I'll talk about why we're interested in this method. And then I'll talk about the Hamiltonian framework, which we use to get energy conservation. And then I'll talk a bit about Upwind stabilization methods, which we use to get a better qualitative field development in our simulations. And then I'll put all of these things together and show a couple of results. And then I'll talk a bit about the operational applicability in the sense of computational efficiency of this method. And then I'll talk a bit about the interpretation of what this energy conservation does for us in the end of the day. Right, so why are we interested in the compatible finite element method? So currently the UK Meteorological Office uses a dynamical core that's based on the Arakawa-C finite difference grid. And that works best if you're using an orthogonal mesh, and for that reason they use a latitude-longitude mesh. But the problem is that that comes with grid poles that lead to computational bottlenecks in the parallelization, and this gets worse and worse as the higher the resolution gets and the more cells you have right around the equator. And so they would like to move away from this grid, and that's why they're interested in the compatible finite element method, which is essentially the finite element version of the Arakawa-C grid, except because it's a finite element method, it allows for more general grids, like a cube sphere grid, for example. And the idea essentially is you pick your finite element spaces. So that's an example of finite elements for a two-dimensional vertical slice of the atmosphere. And you pick the finite element spaces such that they map onto each other via the differential operators that appear in the equations. So for example, the vorticity space gets mapped via the curl into the velocity space. And that space then gets mapped into the density space via the divergence operator. And that then leads to better stability properties of the discretisation, similar to the Arakawa-C grid. And then we also need a temperature space. And the idea here is to pick our finite element nodes to coincide with the finite element nodes of the vertical wind. And that's called the Charney-Phillips staggering, and that has to do with the better representation of hydrostatic balance. So these are the finite elements that the UK Met Office will be using in the next dynamical core called Ganghao, except they'll use lowest order elements, and these are the next to lowest order elements here. And I'll be using these in the examples later on. Right, so we're interested in this parallel efficiency in our numerical weather prediction, but we'd also like to have energy conservation, in particular for our climate simulations. And if you take a look at the underlying governing equations, like the compressible Euler equations with external pressure pi, you find that the energy balance is quite intricate, and it's a balance of the rates of changes of kinetic energy, potential energy, and internal energy, and all of this needs to add up to zero, which is quite complicated. And if you don't do it right, that can lead to net energy biases in climate models. And that's often due to a missing reinjection of kinetic energy into internal energy. And so the question is, how do you discretize your governing equations such that all of these things add up to zero in the end of the day? And one way to do that is using a Hamiltonian framework. And the idea here is that you use the Hamiltonian, which represents the total energy, in this case for the compressible Euler equations, and a bilinear form that's antisymmetric, that's called the Poisson bracket. And so this Poisson bracket takes in functionals, and it returns an expression in terms of L2 inner products of functional derivatives. So for example, for my Hamiltonian H, delta U would just be the flux, rho times U. And similarly, we get expressions for delta rho and delta theta, which then appear in this bracket. And you can then derive the governing equations using what's called the Poisson system, which says for any functional f, we have the f dt is equal to this Poisson bracket of f and the energy h. And then if you pick the right kind of functionals, that then gives us our equations. So for example, if I pick a weak form of the density, so the inner product of a test function and the density, Then on the left-hand side, I get df dt is just test function times the rho dt. And on the right-hand side, I plug in my f in the Poisson bracket. I find df d rho is equal to the test function, delta f delta u 0, delta f delta theta 0. So we're only left with the red box here on the right-hand side of the Poisson system. And so we get our usual continuity equation, because this delta h delta u is just rho times u. And similarly, if we pick the right functional for the temperature, test function times temperature, then everything in the Poisson bracket disappears except the blue box, and that's equal to flux over rho, so that's just u, and we get our usual temperature advection equation. So this is how we get our equations from this Poisson system with the right Poisson bracket and the right energy. And similarly, we can get the momentum equation. And the whole idea is that we want some kind of condition that tells us when we conserve energy and when we don't, some kind of easy to follow condition. And in this case, it's the antisymmetry of the Poisson bracket, because if we plug in as a functional h, the energy, then we have the h dt is just the Poisson bracket of h and h, and by antisymmetry, that's 0. So in other words, as long as we derive our governing equations from a Poisson bracket that's antisymmetric, then we have energy conservation. And that's also true after discretisation. So we just want to find a discretized Poisson bracket that's still antisymmetric. Right, so we can plug this in straight away in our compatible finite element framework with this bracket. And now after the discretization, the difference is that my variational derivatives are now projections into the finite element spaces. So now I don't have the flux, rho times u, but the projection of the flux into the velocity space, and we call it f. And so, for example, my temperature equation now says, rather than plus u dot grad theta, it's plus f over rho dot grad theta equals 0 for my test function gamma. And in this case, we know that this discretization of the compressible Euler equations, we immediately know this is energy conserving because it comes from a bracket that's antisymmetric. And it turns out there's also an energy conserving time discretization called the Poisson integrator, but we'll skip it here in the interest of time. But you can apply it to the system, and then you have a fully energy conserving discretization of the compressible Euler equations. So we can take a look at it and how it behaves. So this is a two-dimensional vertical slice of the atmosphere test case with a cold air bubble that sits in the middle at the beginning, and then it drops to the ground and moves sideways as a density current. And this is the top rectangle is the temperature, and the bottom one is the vorticity. And we see that we do have an energy conservation up to solver tolerance, 10 to the minus 12, but the field development doesn't quite look right. So we have these strange temperature oscillations in the middle, and my density current vortices don't look very good. And the vorticity field is completely contaminated with oscillations. And we'd rather like to see something that looks like this, where you can clearly see the vortices and don't have these oscillations. Now, one way to get rid of oscillations is by applying diffusion. And one way of doing it is by applying diffusion in the direction of the flow. And this method is called upwind stabilization. And that's what we'll be using to get this better field development. And I'll illustrate it for the temperature equation. So it turns out that the type of upwind stabilization depends on the type of finite element space that we use. And in the compatible finite element framework, we use different spaces for our different variables. We have to use a different stabilization for every different field. Now for the temperature, the thing to do is you take your advection term, e dot grad theta times test function, do integration by parts in every cell, and then you get a facet integral contribution for every cell, which you can sum up. And then what you do is you take the value of the temperature that's on the side where the wind comes from. So I call that theta twiddle, and that's what's called upwind stabilization. So for each facet, I take the difference of the test function times the velocity times temperature on the upwind side. And for the temperature field, it's a bit more complicated because I'm discontinuous in horizontal direction and continuous in the vertical direction because of this Charney-Phillips grid. And so I need two different types of upwinding for the two different directions. So for the horizontal direction where I'm discontinuous, I use this upwind technique. And then for the vertical direction, I use something else called SUPG. And the idea is that you take all of your test functions, gamma, and add an upwind contribution to them. And in this case, we only do it in the vertical direction because we only continuous in the vertical direction. And so my fully stabilized temperature equation has this continuous Galerkin upwinding in the horizontal, I call this operator L, and these upwinded test functions gamma with gamma twiddle to account for stabilization in the vertical direction. And then I get this fully stabilized new temperature equation, which has a different advection operator and these modified test functions. And so I would like to have this, but I would also like to have energy conservation. So now I need to sort of somehow combine these two concepts. I would like to have this thing in my Poisson bracket somehow and still make sure it's antisymmetric, because that's what I need for energy conservation. So I take my equation, and the trick is I want to somehow bring it into this Poisson equation form, Poisson system form, because that's how we got the equations in the first place. So I move my upwinded gamma twiddle to the right-hand side. So now it looks like this. And now I'm saying, okay, well, I pick the same f as before in the product of test function and theta. Then my dFdt is this thing again here. And everything else I would like to originate from my bracket. Now, originally, without any upwind stabilization, the corresponding bracket term looks like this in the small blue box. I have flux over rho, that's u, so u dot grad theta, in other words. But now I'd like to have this instead. So I just take my Poisson bracket term and replace it by what I need to arrive in the end of the day at this term. So I have my advection operator L, and then I have this gamma twiddle d theta dt contribution here. And now instead of test functions gamma, I have df d theta, and I have some kind of advecting velocity here. So now I have this upwind stabilized term in my Poisson bracket, but I also want to make sure it's antisymmetric. So I look for the corresponding antisymmetric term that I had originally in the small gray box. So that's the same one as this one, just f and h is switched and plus and minus is switched. And then I do the same treatment here. So I change this Poisson bracket term to an upwind stabilized version. And then I look for the antisymmetric term and do the same thing. So these two terms in gray and blue are the same thing, except f and h is swapped and plus and minus. So I still have an antisymmetric bracket, but it now includes upwind stabilization. So it should stabilize my field, but it should still be energy conserving. That's the idea. And it turns out this gray term ends up in the velocity forcing equation. So I'll have a different forcing term. So we can have a look at if that works. So that's the same test case again, this falling bubble that then floats along the ground. And the left column is without upwind stabilization, and the right column is with stabilization. And we find that, as expected, these spurious, these unphysical oscillations largely disappear. So that's nice. And we also still conserve energy. So on the left-hand side is what would happen if I included this upwind stabilization, but not in any Poisson bracket kind of sense, in a sort of non-energy conserving sense, if I just introduced it and didn't care about energy conservation. And then my energy error goes to the order of 10 to the minus 6. But if I use my Poisson bracket framework, I stay at 10 to the minus 12, whether or not I use this stabilization. Okay, so that's good. We now have a good field development, and we also have energy conservation down to solver tolerance. But now the question is this actually a sensible thing to do? What happens, for example, with the computational cost? And there's two main things to note here. The first one is, in the end of the day, you get a nonlinear system of equations, and you need to solve that with a Newton iteration scheme. And the Newton iteration scheme itself is not energy conserving. So my energy error depends on the number of Newton iterations. That's 4 iterations in blue, 5 in purple, 6 in red, 8 in green. And ideally, numerical weather prediction, we usually only use 4 of them. And with this plot here, I think I used 32. So you need a very big number of Newton iterations to actually get to this degree of energy conservation, which is quite wasteful. So the question is, what happens if we only use 4 iterations? That's the first thing. And the second thing is, it turns out if you use this energy conserving setup, you need additional auxiliary equations to do for every Newton iteration. For example, you need to compute these Hamiltonian projections. And it turns out in this fully upwind stabilized setting, you need 5 of these auxiliary equations in every step, which is quite expensive. So the idea is, let's do some kind of approximation to get to something that's cheaper and it still is worthwhile if you only use 4 Newton iterations. It turns out you can do an approximation of the time discretisation. This is how the energy conserving time discretisation for the flux would look like. If you do something slightly similar, slightly easier with midpoint time averages, then it turns out you can do some swapping around and most auxiliary variables that you need drop out, and you're only left with 2 remaining projections. One of them is for the variation in rho, delta H delta rho, with some time average, and one is for delta H delta theta. But because this is a DG space, it turns out for lowest order finite elements, this is just an inversion of a diagonal matrix, and this is an inversion of a tridiagonal matrix because it's continuous only in one direction. So in other words, if you do the simplification, and if you only do 4 Picard iterations, Newton iterations per time step, then this approximately energy conserving scheme is only marginally more expensive than a comparable scheme that wasn't derived in a Poisson bracket framework and an Hamiltonian framework. So we're sort of looking at an equal kind of cost scenario. So let's do the comparison here. So on top we have a fully stabilized compatible finite element scheme without any regard of energy conservation. And at the bottom we have this approximately energy conserving scheme that's also fully upwinded, fully upwind stabilized, and only marginally more expensive, only I think 4% per Newton iteration more expensive. And it turns out, even though the cost is comparable, we still get a better accuracy in our energy of 1 order of magnitude in comparison to the non-energy conserving stabilized scheme. And this 1 order of magnitude is enough for us to have a different field development. So in this main vortex of this density current that flows along the ground, we have additional small shear vortices that arise because of this better energy accuracy. So that's good news. But now the question is this actually something we expect to see? Is this something physical? Is this the right thing? And it turns out people have seen something similar in the literature, namely in the subgrid scale literature. And there was one paper published in 2015 by Maras, Nazarov, and Giraldo, where they compare subgrid models. And in this case, they're using a spectral element method. And the idea with subgrid scale models is that you apply a spatial filter on your equations, and then you get an additional term in your equations that corresponds to the subgrid scale. And this you can then discretize in various different ways. And one of these ways is called the Smagorinsky subgrid scale model, which essentially discretizes this term according to sorts of physics-based heuristic. And then this new model that I proposed in 2015 is called the dynamic subgrid scale model, where the idea is that the subgrid resolving term is based on the size of the residual of the equations in every time step. So in other words, if the residual of the equations is bigger, then that sort of means the equations are worse resolved. And so they increase the size of this subgrid term. And then they get essentially the same result as we do, namely they get these additional shear vortices. So this sort of suggests that in our approximately energy conserving scheme, the energy is reinjected correctly to produce these subgrid scale features. But I should say that this is still a fairly active area of research, because it might just be that this sort of happens randomly or by accident. So we still need to show that there's actually the correct underlying mechanism that produces these subgrid features in our energy conserving setup. But it's looking promising in any case. So to summarize, we have a compatible finite element discretization that's fully up and stabilized and energy conserving. So we remove these unphysical oscillations, and we can still have energy conservation up to solver tolerance. And we can come up with an approximation, a simplification that gives us a scheme that's only marginally more expensive than a comparable non-energy conserving scheme, but still produces these features that can be seen as subgrid scale features potentially. And yeah, that's it. Thank you.
Thank you very much, Golo.
Okay.
Was a very interesting talk.
Sorry?
So what happens if you play with the resolution to determine whether these, what looks like sort of instabilities in this curl up are physical or not?
So if you make the resolution finer and finer, you'll get more and more of these.
Okay, so you would expect that they exist.
That's right, yeah. Yeah. I should note that this kind of test case usually comes with an additional diffusion term so that the solution converges to something. And then people usually compare this converged solution. But in this case, they turned off this diffusion term just as we did. And we turned off the diffusion term to focus on energy conservation, and they turned off the diffusion term to see what happens with these subgrid features. Yeah.
So where does the energy actually go? So you don't have explicit subgrid terms or a subgrid energy budget. That is right. So it's simply in the numerical scheme, because of the way you derived it, it's intrinsically energy conserving.
That's right. Yeah. So for example, for the temperature scheme, it's you have this stabilization in here, which corresponds to temperature advection, and the corresponding antisymmetric term shows up in the velocity forcing. So somehow you have this interplay between velocity forcing and temperature advection. And I should note that you can also express these rates of changes of kinetic potential and internal energy with respect to these Poisson bracket terms. And I think this pair that I just showed you shows up in the internal energy rate of change and kinetic energy rate of change.
So you actually convert kinetic to internal energy. If you have a downscale, let's say locally, some downscale cascade, so the energy has to go somewhere, right? So you can't keep it in the kinetic energy, so it gets converted to the internal energy budget.
Exactly, yeah. So this pair here is purely an interplay between kinetic and internal energy. That's right. But how exactly that works is a bit unclear still. So, for example, spatially, how that works spatially, which amount of internal energy goes to kinetic energy.
But in some sense, you depend crucially on the compressibility. So if you tried the same tricks for incompressible flow, then you would run into some barrier of unphysical behavior, I suppose, because the energy has nowhere to go. You're forcing to conserve it, and it has nowhere to go when it should cascade downscale. Is that right?
That sounds right, yeah. It would be interesting to see what kind of Poisson bracket structure there would be, if any, for incompressible equations. I think for the incompressible equations, you need some kind of Lagrange multiplier in here that enforces the incompressibility. And then I don't know how these balances would look like, but it would be interesting to consider.
Right. Do we have other questions? So how close are you to what is actually done in the Met Office?
That's a very good question. So fairly close in some sense, not very close in another sense. So if you look at the Poisson bracket, this term here is like a vector invariant form of velocity advection. Mm-hmm. And that's exactly what they do. And then you've got two forcing terms in the velocity equation. And then you have two advection terms, namely one for density advection and one for temperature advection. And at the moment, they have both a finite element and a finite volume scheme implemented for temperature and density advection. And I'm not sure it's completely clear yet what they use, which they'll be using. But if they use a finite volume scheme for example, temperature advection, then they'll have a finite element set up for this forcing term and the finite volume set up for this advection term. And then it's essentially impossible to keep up this antisymmetry. So if they end up doing that, then I think it would be hard to implement the setup. Mm-hmm. But if they choose to go for the finite element advection schemes for temperature and density, then I think they could absolutely implement this just fine. And I'm pretty sure they'll use a finite element scheme for this vector invariant part. So there they can definitely use that too. So what they would have to do is then compute this projection here to make sure. I think they actually do that. So I think the way the velocity advection scheme is set up at the moment is energy conserving. But here it depends on the choice of finite volume scheme or not. And then it becomes nearly impossible to set this up.
Okay. And what you've shown so far, that is fully 3D, or is it just a two-dimensional cross-section?
So this is a two-dimensional test case, but the framework essentially works just fine in 3D as well. So I'm working on a three-dimensional case at the moment. And here my focus is on this vector invariant form, because essentially we haven't really found a satisfactory vector invariant advection scheme yet for these compatible finite elements. It's a bit tricky. The question is, do you maybe do some kind of vorticity advection scheme and then use the vectored vorticity in here, or do you replace the vorticity by the curl of U and then do some kind of upwinding here? That's unclear at the moment. And the idea is to study that in 3D. Yeah. But as it is at the moment, it could be readily used in 3D. Unfortunately, these 3D simulations are quite expensive, so I always have to wait for quite a long time to see what's happening.
Right, and the physics might be different after all if you look at least at fully turbulent flow.
Yeah, exactly, especially
in terms of the cascade structure.
Exactly, yeah, that's very true. For example, in 2D, here the right thing to dissipate would be the entropy, but in 3D that's not so clear anymore, and it's not even clear what would you dissipate in this velocity vorticity advection term in 3D. So currently we're trying to use an SUPG scheme for the vorticity and see if that works. But yeah, still some way to go there.